Yeah, we have few questions, sir. So the first question is, what is the difference between
Yes.
general theory of relativity and special theory of relativity?
All right. This is a very big question, Arti. This is a very nice question. The special theory of relativity uh, did not take into account gravity. And the way it is done is if you go back to one of the slides, so let me see if I can get back to that point.
Hmm.
I would like to answer this question using what we have discussed today rather than bring in anything which is outside today's discussion because this is a very big subject. So I have gone back to my slide number 20 in which I was discussing this uh, distance between 2 points in the space-time continuum. Are you able to see the slide now?
Yes, sir. Yes. Yeah.
All right. So I refer to the Pythagoras theorem and and I raised this point that okay, the distance between 2 points, a plane on a two-dimensional plane like the xy plane
Yes.
is dz square, which is equal to dx square plus dy square in the usual Pythagorean geometry, right?
Yeah.
So
Yeah.
relationship that everybody is familiar with. And you can extend this from a two-dimensional plane to a three-dimensional Euclidean space.
Huh.
But now, when you go to the space-time continuum, you have a four-dimensional continuum, which consists of the space and the time both.
Yes.
And in this, you have got a similar quantity, which is metric, which is like the distance between 2 points, but these are not the points in space, these are points in the space-time continuum, or what is sometimes called as the Minkowski space.
Okay.
And in this, the ds square is given by this relationship which I have on this screen.
Hmm.
And the G matrix, this is the one which has got the signature of the space. So this is a space-time continuum. It is four-dimensional. Mu and nu both go from 0 to 3. So 0 is included. So there are four coordinates. Um, and the properties of the space-time continuum are contained in the G matrix. So this is a 4 by 4 matrix, and its elements are what are given over here. So it has got diagonal elements, all are equal to 1, but three of these have got a negative sign and one has got a positive sign. It can also be the other way around. You can have one negative and three positive, but uh, three have to have a sign which is different from the fourth, and that is important in this context. So when you write Euclidean dz square, which is dx square plus dy square, the sign of dx square and dy square are both positive, but that is not what will happen in a space-time non-Euclidean Minkowski world. So this is the four-dimensional space, and this is the space which is called as the flat space-time continuum. This is where the special theory of relativity and the general theory of relativity are different.
Okay. Okay.
So minus one, minus one, minus one. So this is called as the signature of the G matrix. And this signature belongs to a flat space-time continuum. In the general theory of relativity, you do not have what is called as a flat space-time continuum. You have got a curved space-time continuum instead of the flat space-time continuum. And what it means is that these elements 1 and minus 1 are different. And in the general theory of relativity, you accommodate different values over here, and there are different approximation schemes like the Schwarzschild approximation and so on. So that's a matter of detail, and I will not get into that. But the G matrix is different, and then you get a theory of gravity. Uh, so you interpret acceleration and gravity um, in terms of geometry. So those are the additional consequences of the general theory of relativity. They come from the curved space-time continuum. It has got more general geometry,
Okay.
and that is not the property of the special theory of relativity, which certainly deals with the constancy of the speed of light, the time dilation is accommodated for, the Lorentz contraction is accommodated for, and these are all intrinsic elements of the fact that the speed of light is constant in every inertial frame. So the general theory of relativity has a far more general uh, G matrix which belongs to the curved space-time continuum.
Okay. Okay, sir. Thank you.
Yes.
Okay. The
Any other
next,
question?
yes, sir. So the next question is, if current is just flow of electrons due to the potential difference between 2 points,
Mhm.
then is it gravity?
Well, uh, it I think I understand. If I understand the question correctly, uh, what the person who has asked this question having in her or his mind is that you have a potential difference in the field as which makes it which enables the transportation of the charge from one point to the other, from a higher point, from a potential of from a point of higher potential to a point of lower potential. And similar thing happens to a mass in gravity. It moves from a point of higher potential to a point of lower potential under gravity. So there is a certain element of similarity. I think one should not carry this similarity too far, because the gravity that we are talking about over here is the Newtonian gravity, which is like instantaneous. It has an effect at infinite distance uh, instantly, but that is not something which accommodates the fact that okay, that physical influences do not travel at infinite speeds. The speed that anything can attain is the speed of light. Even for light to reach the earth from the sun, it takes more than 8 minutes. And if you switch off gravity between the sun and the earth, if the suggestion is that the effect will be instantaneous, then it is very misleading. So one should not carry these similarities too far, because gravity is a much more complex thing than what Newtonian gravity makes us believe.
Yeah. Yes. Yes, sir. Thank you,
Mhm.
sir. Yeah. The next question from the chat box. Can you
Mhm.
briefly explain Arnold effect?
All right. Now, this is a very nice question. The Harnabaum effect is really what makes electromagnetic potential so important. And normally, when we talk about electrodynamics in classical physics, we normally think about the effects generated on charges and currents by the electromagnetic fields. The governing relationship over there comes from the Lorentz force. And force, idea of force, is not so much used in quantum theory. In quantum theory, you write down the Schrodinger equation. It has the Hamiltonian operator. It has got the potential energy operator. So it deals with potentials. It does not deal with forces. So in the Aharonov-Bohm effect, and let me see if I can pull out that slide
Yeah.
which I used for this. So I think it is over here.
Yeah.
Here in the Aharonov-Bohm effect, you have got an electron gun over here. Can you see the slide?
Yes. Yes, sir. Yes.
All right. So you have got this electron gun, and you have got electrons which are ejected from the electron gun, and they may go through either of the two slits. And this is what makes it like an optical Young's double slit experiment. The electrons can go through either slit 1 or slit 2, and the pattern that they generate on the screen at the detector is essentially one of interference. And this is coming from the quantum interference because it is the probability amplitudes which are complex, and they add up with magnitudes and their phases, and depending on how the superposition takes place, the intensity pattern comes from the square of the superposed probability amplitude. So first you must add up all the complex amplitudes and then take the modular square of that to determine the intensity. So in the Aharonov-Bohm effect, you have got the same experiment, except that you do a small modification. And this figure is not to scale, but there is a solenoid over here which you keep right behind the slits. So right behind this gap between the two slits, you have the solenoid, and therefore the electrons which go from slit 1 are going behind this solenoid, and the electrons which are going from slit 2 are coming in front of the solenoid. Okay, so that's the geometry in this experiment. And the interesting thing of this experiment is that if you pass a current through the solenoid, we know that the magnetic field is solenoidal, which means that it is divergence free, and the entire magnetic field is essentially inside the solenoid. Outside the solenoid, the magnetic field B is absolutely zero. What it means is that the electrons on either of this path, the path which is behind the solenoid or the path which is in front of the solenoid, neither of these electrons have any chance of coming across the magnetic field. The magnetic field in their path is essentially zero. The entire magnetic field is inside the solenoid. And therefore, if we go by the classical idea that it is the fields which are of importance, they are the ones which exert a force. And this is the idea which is being modified now in quantum theory. It's not the fields which are important, but the potential which is important. So this field would have no effect on the electrons because their paths do not meet the field at all. However, what happens is that if you see the pattern on the screen, on the detector, then this pattern over here, the fringe pattern, is shifted. And this is what is shown in this part of the figure. Where you had the bright fringe, you may get a dark fringe, and vice versa. So the reason this is happening is because of the potentials. The magnetic field is zero, but the potential is not. And the potential generates a phase difference which goes according to this relationship. So this is a phase term which comes in, which is sometimes called as the Berry phase after Michael Berry. And this can be very nicely discussed in using the Feynman path integral approach, because that explicitly refers to the difference in phases, and it is this phase which generates a phase difference and an eventual moderation of the interference pattern. So that is the Aharonov-Bohm effect. It is the effect, it is a quantum effect which is coming from the electromagnetic potentials. The fields become secondary. So that is essentially the Aharonov-Bohm effect. Yes. Next question. Hello? Hello?
Hello, sir.
Yes. Did
Yes.
you
Yes,
get
sir.
the full answer?
Yes, sir. Yes, sir. Yes, I got it, sir.
All right.
Yes, yes.
Okay. Good. All right. Good.
Yeah, yeah. One last question for the session, sir. Uh,
Yes.
can you give us a practical example of length contraction and time dilation?
Your voice is breaking. I cannot hear you.
Okay. Okay. Sir, can you give us a practical example of length contraction and time dilation?
Oh, sure. Uh, this is this can be seen actually. You can see the consequences of this even in your lab, you can set up these experiments in your lab, in your schools and colleges. It is not going to cost you a lot of money. Some of my students set up this experiment in the laboratory of the IIT Tirupati recently, and we wrote a little paper on this in resonance, so one you can get the details from there. And in this experiment, what you're going to see are certain tracks which can take place only because of muon decay. And the interesting thing about it is that these muon decays take place in the upper atmosphere at a large distance. And unless you take into consideration the length contraction or the time dilation, there is no way you can see these tracks in your laboratory, which is on the ground. The
Okay.
fact that you're able to see these tracks in your lab means that the products of these decay are actually reaching your lab in a finite amount of time, and the amount of distance they carry is otherwise so huge. But in the frame of reference of these particles, which are traveling at huge speeds, at near relativistic speeds, they experience Lorentz contraction, and the distance is not as much as it would seem from our frame of reference if we are just sitting in the lab. So that is an effect of time dilation and length contraction, and there are many examples. You can carry out experiments in jet planes, and many of these experiments have been carried out, and this is a matter of hard reality. Even your GPS system in your cell phones works because of this, because the time dilation and length contraction is properly accounted for. As a matter of fact, it's not just the special theory of relativity. Even the corrections due to the general theory of relativity have to be taken into account,
Okay.
so that cell phones and the atomic clocks are appropriately calibrated so that your cell phones will work. So um, the fact that the satellite communication that we are using for this webinar, this is taking place over the internet, and there are these atomic clocks which govern this communication. So all this, an immediate consequence of the fact that the effects of the general theory of relativity and also the special theory of relativity, namely the time dilation and the length contraction, is operating exactly the way we know from Einstein's theory.
Okay. Okay. Yes, sir. Okay.
Yes,
Yes. Thank you, sir. So there are a few other questions, and we will mail you for answers, sir.
sure.
So thank you very much for the lecture. Thank you, sir.
Okay, goodbye.
Yes, sir. Bye.
Thank you very much.
Yes, sir. Bye.